Good afternoon, everyone. Welcome to Facebook Live from the SETI Institute in Mountain View, California, and scattered around as we still are. My name is Simon Steele. I'm the senior, I'm not the senior astronomer. I'm going to talk to the senior astronomer. Maybe I want his job. I'm the Senior Director of Education and STEM Programs at the SETI Institute. And joining me today is Seth Shostak, the Senior Astronomer at the SETI Institute. And we are going to take a little journey back in time, about 100 years, to Washington and the Smithsonian National Museum of Natural History. It's going to be the 26th of April, 1920. I'll get my centuries right. And Seth, we are going to be looking at how the universe looked 100 years ago, and especially about a debate that tries to determine exactly what the universe is and how big it is. Maybe to start with, tell us a little bit about the state of the universe 100 years ago, if we were back in 1920.
Yes, well, to begin with, the cars would have looked a little different, but the universe, of course, was pretty much the same, but our ideas about the universe certainly weren't the same. To begin with, if you said, okay, what is the universe? That meant, back in 1920, that meant the Milky Way galaxy. The universe was one giant flattened disk of stars called the Milky Way, and that was it. That was the entire universe. And but there were, glimmers that maybe that wasn't quite right, and that's what spawned, really sort of spawned this debate. There was a debate about the debate, actually, because some people were saying, hey, this debate should be about relativity, right? Einstein's theories of relativity were still new back then, and but then they thought, well, the public isn't going to understand that. Let's talk about the size of the universe.
Okay, and welcome everybody to this debate on the debate on the debate. If you do have any questions, please do send them in, and we'll try our best to answer them. Let us know where you are watching in from. We have a viewer from Kurdistan already. Welcome. So it seems that when we go back to 1920, the sun is back at the center of the universe, in a sense. It was sort of this whole Copernican idea, or anti-Copernican idea, that where is humanity? Where are we in terms of the universe as a whole? We've already been displaced from the center of the solar system, but we're still in the center of the Milky Way, center of the galaxy.
Yeah, I think everybody likes to think they're special. And so we were still special. Some people said, yes, we were still near the center of the Milky Way. But the other big question was, okay, if the entire universe is the Milky Way galaxy, how big is that, right? And, it's often very difficult to work out how far away things are. And in astronomy, if it's something close, you can just use the geometry that the Greeks worked out about 1,300 years ago, 2,300 years ago. Having trouble getting my millennia straight. Yeah, so you could do that. But if you're talking about something that's far away, farther than the nearest stars, even the nearest stars is hard. You can't just use that geometry. It doesn't work too well. So, there was a big debate about, well, how big is the Milky Way galaxy? For those who are taking notes, both of you, the Milky Way galaxy was figured at that time to be roughly 30,000 light years across. And as you say, Simon, the sun was more or less in the center of that. So, 30,000 light years for the entire universe, and we're in the center. Not so bad. I mean, you have easy access to the food markets.
I mean, that's still a big galaxy, and if you're putting things into perspectives, how much, how big Rhode Island is, or England, 30,000 light years. This is big. So it's not as if we're talking about a tiny little, solar system sized thing. But when you get up to these distances, it's very, very difficult to measure how far away stars are. And I think that's the problem, isn't it? So Seth, just to get back into the discussion on the debate, would you like to say a little bit more about the protagonists in this debate? Who's in the blue corner and who's in the red corner?
Yes, indeed. There were two of these guys. They weren't the original choices, but they were considered to be the better choices eventually. And one was a guy from Southern California, Harlow Shapley. He worked at the Mount Wilson Observatories run by Caltech. And the biggest telescope up there, at least in 1900, by 1920, it was about to change, was the 60-inch reflector. So that's a 5-foot mirror. If you lay on the mirror of that telescope, not a good idea. But if you'd done it, your feet would hang over the edge. Down sorry, that was in Southern California. But in Northern California, the guy was a fellow by the name of Heber Curtis. And he was using the Lick Observatory telescopes, the biggest which was the Crosley reflector. And that's a 36-inch mirror. So if your big dog was lying on it, you know, his feet would hang over the edge. These are, by modern standards, pretty small instruments. But this was an all California program. And these two guys were there to debate basically how big is the universe.
So let's turn to Harlow Shapley in the red corner first of all, and what was his basic argument? And I know apparently he was under pressure because they had people from Harvard watching him. This was almost a job interview for him, I believe. So no pressure there. So what was his basic premise?
Yeah, you're right. This was kind of a job interview for Harlow Shapley. He did get the job, by the way, but he was not a very accomplished speaker. So he was nervous. He read from notes. His opponent, Heber Curtis from Northern California, it was Northern California versus Southern California. The guy from Northern California was a pretty good speaker, so he didn't need to use the notes and so forth and so on. So in some ways, he came across a little bit better. But here was their points of view. Harlow Shapley said, look, my job and what it is too is I study the size of the Milky Way galaxies. And I've been looking at these clusters of stars, they're called globular clusters. And on the basis of assuming that they're all, you know, similar to one another, you know, they're sort of like, I don't know, tigers. They all kind of look alike, right? He was able to judge how far away these things were. And he said, the bottom line there is that the galaxy is not 30,000 light years across, which was the common number, but it's 300,000 light years across. That's a big difference, okay? That's what he was arguing. And so he said, you know, these little smudges you find on photos made of the sky with, you know, long time exposures, these little smudges, they have to be inside our galaxy, you know, balls of gas, disks of gas, something, because the galaxy is so big, they couldn't be beyond that. Mm-hmm. Heber Curtis from Northern California said, no, I think that's wrong. He didn't argue about the size of the galaxy so much, but he said that those little smudges, they're way beyond the edges of the Milky Way. And those are other galaxies. And we live in a universe in which the Milky Way is just one of many.
Mm-hmm. And he introduced the term island universes, didn't he? As a concept for these galaxies, and that these are Milky Ways in themselves. But there's a problem, of course, with that, because we'll get back to errors and bits in a minute. But Harlow Shapley's estimate, I mean, this is 10 times bigger than the galaxy was before, which, if that's true at 300,000 light years across, and these other smudges are also 300,000 light years across, that puts these other galaxies at incredible distances that people weren't happy with. So I suppose, I don't know, is it almost time to bring in another person, another technology, Seth, to try and answer these questions definitively? And the technology is, or the objects I'm thinking of is Cepheid variables. And the other name to bring into this conversation is Edwin Hubble.
Yes, well, absolutely. I mean, this debate wasn't really a debate. You know, each of the speakers got something like 30 minutes to present their case. And so one guy gets up and he says, oh, well, this is the size of the Milky Way, and, you know, it's big. And the next guy gets up and he says, well, yeah, it may be big, but I think these little smudges are galaxies, island universes. Remember, island universe, that's not something like a reality television show. Island universe just means it's another galaxy, right? Because a galaxy was a universe back then. It's just a semantic point. All right, so he was saying that. And the question was, well, who won the debate? And at the time, people thought that probably Shapley won the debate. In other words, the galaxy was so big, those little smudges couldn't be external galaxies. That would have been the wrong answer. But to say that he won the debate is probably unfair. And nobody really won the debate. But you're right. 3 years later, this guy, Edwin Hubble, who had considered a career as a wrestler, professional wrestler. As it turns out, he wouldn't have had a telescope named after him if he had been a wrestler. But he was making pictures of a nearby galaxy called Andromeda, but it wasn't called a galaxy then, it was just the Andromeda Nebula. It was just a cloud in the sky of stars. And he found a variable star in there. And that was the clue to figuring out how far away it was, which he tried to do, and came up with an answer that was, I think, like 750,000 light years, 800,000 light years. And that meant island universes.
So say a little bit more about these stars are called Cepheid variables after the first star of its type was found in the constellation Cepheus, and that's where they get their names from. And these stars have a property actually that has been so critical in our understanding of the universe since that moment. And the first person to study Cepheids was a woman astronomer, Henrietta Leavitt, who was at Harvard College Observatory. And say a little bit about Cepheid variables, not the technical details, but what properties do they have that make these things useful?
Right, exactly. If you want to find the distance to something and you have no other way to do it, you can kind of assume how bright you think they are, and that'll tell you how far away they are. Now, that doesn't not make much sense, but think about it. If I take a 100-watt light bulb and I put it 10 feet away from me and I have a light meter or something and I measure how bright it is, and then I put it 20 feet away from me, it'll be 1/4 as bright because it's twice as far away. Okay, so if you just measure the brightness of something, you might be able to tell how far away it is if you know how bright it is intrinsically. You know that it's a 100-watt bulb and not a 500-watt bulb. By the way, I might point out that behind Simon there, you see a bunch of galaxies. I think that's Stefan's quintet.
It is, yes. A Hubble image, yes.
Yeah. Yes, I've been involved with studying that particular place. If you look at the galaxy, and we know it's a galaxy, to the upper right there, it's sort of 2 o'clock on Simon's head. That's NGC 7320, in case you need to address it by its name. And the question for years was, how far away is that compared to the other galaxies in that picture? And they all look about the same size, so maybe they're all at the same distance. Wrong. That NGC 7320 in the upper right there is 10 times closer than the other guys. So even 20 years ago, we couldn't figure out the distances to galaxies very well. But this is all a sideshow. Let me get back to Henrietta Leavitt. She was indeed Harvard College Observatory, and they sent her down to South Africa to study the Small Magellanic Cloud or whatever. And she found these stars in that cloud, Cepheid variables, that would get brighter and then dimmer, and then they get brighter and then they get dimmer and they get bright because they were different sizes, it turns out. But what she figured out was you could tell, their brightness on the basis of how long it took them to get bright and dim, right? If they did it very quickly, one day they're bright and the next day they're dim, then they're bright again, dim again, then they were kind of dim bulbs. If they took days to get brighter and dimmer, then they were very big stars. That was the key for Edwin Hubble to figure out that Andromeda was 800,000 light years away. Not that she gets much credit. She was a woman working in astronomy, and back in the early part of the 20th century, she was sort of overlooked.
But of course, Shapley then went to Harvard College Observatory, and so, and of course, Shapley's connection with Cepheids as well, because he used and maybe used them not quite accurately to even get his number for the size of the Milky Way, didn't he?
Yeah. I mean, these guys would use any technique they could. I mean, some of them were very simple, just by like saying, as I just pointed out behind you, those galaxies all look roughly, within a factor of 2 or so, they all look pretty much the same size, right? So if somebody asks you, okay, you're driving up the freeway here, and you see that car way up there, how far away do you think it is? Without any instruments, what you'd say is, well, it looks like it's about that big. And I know how big cars are, they're 6 feet across or whatever they are. You look at them head on. That gives your brain some idea of how far away it is. So, yes, Shapley was using those arguments. They all were. I mean, they didn't have any other things to go by, but it was the case that with these little smudges, which they were really trying to figure out the distance to, they were all sizes on photographic plates. And we now know the reason for that is the universe is filled with galaxies, and some are near and some are far. So some look small and others look big.
So this was first of all, from the Great Debate, and then from Hubble's work, this is a double whammy of the removal of humanity from the center of the universe, isn't it? Because not only are we not the center of the galaxy, in fact, the galaxy isn't even the universe. It's just one of 10 to the 10 known galaxies in the observable universe. And then, how big is the actual universe beyond the observable universe? So it really was the beginning of the understanding of the sheer size of the universe and our removal of that special place in the center.
It's been called, this whole thing where we found out that the universe had galaxies in it. And I think the current number is like 2 times 10 to the 12th. So that's like 2 trillion galaxies in the visible universe. I mean, that's a lot of galaxy pleasure, right? And it removed us not only from the center, I mean, there is no center, and we're just another galaxy. So philosophically, you know, you could say, all right, this is the final blow. It's, you know, we're just not all that special. And of course, it's possible, but there's no real evidence yet, that there are other universes. And I can well imagine that 20 years from now, they'll say, what are these guys talking about? You know, are there other galaxies? Come on, there are other, you know, it's a multiverse. There are all these other universes, and we're not even, you know, the most important of the universes. So, you know, when you walk through these, to the shopping mall, figuring you're really special, reflect on this.
Yes. So actually, most of the questions that have come in are about the universe beyond the 1920s, 1930s universe we've been talking about. This is a question from Jerry. Given the relativistic nature of space and time, what can we really say about the size and the age of the universe? So tell us a little bit about the size and the age of the universe, Seth, as we know it now in 2020.
Yes, right. Well, if I could say something interesting there, they'd probably fly me to Sweden for a prize. You know, well, look, the age was originally actually worked out. Even Hubble could do that. He said, okay, I found that the universe is expanding. He found it out by mostly using other people's data, but he was clever enough to make a plot showing that the galaxies were all receding from one another, or mostly were. And so you can imagine that it's like somebody, you know, pulls the pin on a hand grenade inside your living room, never a good idea, offends the host. But if you do that, you'll notice immediately that all, you know, everything is racing away from you, all the fragments. And all you have to do is measure the speed at which they're racing away from you. You can work backwards, run that movie backwards, and now you know when somebody pulled the pin. So that gives you the age of the universe. And that has been argued back and forth because of difficulties in the measurement for decades. But the current number, which is derived from very much more subtle arguments, is roughly 13.5 billion years. So anybody in the audience who's watching this who's more than 13 billion years old will remember the Big Bang and the start of the universe. Now, as far as the size, all bets are off. Nobody knows. I mean, we can see obviously only things that are no farther away than about 13 billion light years because there hasn't been enough time for them, for the light from those things to get to us. We don't know how big the universe is. Some people think it's finite. That is, you could just count up everything and that was it. Here's the number. This is how many galaxies there are. And there are other people who say, nope, it's probably infinite. And at this point, I don't think we know.
And this is a subtle distinction between what we mean by universe with a capital U and observable universe, because of the only way we can actually really observe the universe currently, maybe gravitational waves is another way that, you know, we can bring in, is with light. And that light travels at a finite speed. And on the universal scale, it's not very fast. It's sort of just going at rather sort of slowish pace of 300,000 kilometers per second, which means that we can only see objects 13.7 billion light years away, which is when that light was emitted and traveling to us. Now, of course, since that time, those objects that have emitted that light have actually moved further away. So the actual physical space we're seeing is bigger than that. I think it's about 45 billion light years in rate, something like that. But who knows beyond that, because we haven't got that information.
Yeah, exactly. And people will occasionally ask, they say, no, wait a minute, all right. So, you know, nearby galaxies are moving away from us at a couple of 100 miles per second. It was pretty rapid clip, but farther galaxies are moving away faster. And if you look at the more distant galaxies, I mean, the ones behind you are moving away from us on the order of 700 or 800 kilometers per second. You know, but if you look at the small little galaxies that are in that photo, they're moving away from us at thousands of kilometers per second. And eventually, if you look far enough away, they're moving at almost the speed of light. But what about the galaxies beyond that? Because there surely are some. In fact, maybe most of them. Are they moving faster than the speed of light? That sounds like something that shouldn't be allowed, like, you know, going to the beach. All right. Well, the thing is, you don't have the right attitude, as they used to say in Philadelphia. The point is that it's not that the galaxies are actually moving through a big dark room, right? That the Big Bang was a little, you know, here, I'm going to pull a pin on this hand grenade and all these galaxies, you know, form and start expanding in a big dark room. They brought space with them. Space is part of the universe. It also began with the Big Bang, and it's space that's expanding, not that the galaxies are moving through an empty space. So they're allowed to go faster than the speed of light relative to one another.
So they're not actually moving, it's just the space between them is getting bigger.
It's filling up.
Weird concept around
Yeah,
that.
but like the, you know, the raisin pudding model, right? You know, you raisin pudding and you put it in the oven and it all expands and every raisin gets farther away from every other raisin.
It's a good experiment to try at home. Never works for me. A question from Roman, and maybe this is now we're talking about Hubble's work rather than Shapley and Curtis, but he talks about the big crunch. Now, the big crunch is less talked about these days. What is the big crunch? And maybe that's something to do with food as well.
Yeah, no, that's right. It was always in my lunch box. It was always a big crunch there at the bottom. No, the big crunch was, and particularly, this is, as you say, somewhat of an antiquated idea, but the galaxies are all moving away from one another. But of course, they're also all pulling on one another, right? There's the mutual gravity. So they should all be sort of slowing down. The expansion should be slowing down. And the question is, well, will it just keep on slowing down but never get to zero? Or will it slow down, get to zero, reverse direction, and then all the galaxies will come together in a big crunch and maybe just start another big bang and, you know, we'll come up with a whole new universe. That depended only on, you know, the density of stuff in the universe. But all of that has changed in the last 20, 30 years because it, you know, there's something called dark energy that's blowing apart the universe much faster than we thought. It's accelerating. So it looks like the big crunch is not in your future. You know, probably don't have to worry about that happening to you, that you go out every night and the galaxies are getting closer and closer until you're in a very hot fireball, at which point all your real estate investments are worthless.
So I have a couple more people listening. A question from Don, how big is infinity? We'll save that for the episode 2. Arlington, Virginia, Sao Paulo, welcome. Pakistan, welcome to listeners. Somebody from Holland as well. Let me see, what have we here? A question about black holes. Could black holes in our universe be the beginnings of big bangs for other universes? I'll leave that one for you, Seth.
I don't know. I mean, people like that idea, but on the other hand, I mean, there's something to it in the sense that making a big bang, you may wonder, how do you make a big bang? You know, it's going to be your science fair project for next year. Apparently, it's something that in theory you could do. And maybe it happens in the extreme conditions of black holes, possibly. You know, I haven't ever seen a paper where it says black holes are the big bangs for new universes. But there is something called, you know, continual inflation and so forth, where in fact you do make big bangs. And in fact, there's even a book, I forgot who wrote it. It was some young woman physicist wrote a book on how to make a, you know, a big bang in your basement kind of thing. You can make one at home. One of the essential ingredients, however, and you don't need much, it turns out, but you do need a magnetic monopole. And without going into what that is, let me simply say that if you have one at home, write us.
Yes, we got use for those. A question from Nelson. We can see the microwave background. We haven't talked about the cosmic microwave background, which is the leftover heat from the start of the universe, from the Big Bang. How much of the universe is visible and how much is it invisible? And of course, that's you know, what do we mean by invisible, I suppose?
Yeah, well, that's maybe when people ask you what are the biggest science discoveries, at least in astronomy, in the past 30, 40 years. One of them, of course, is the fact that planets are very, very common. We didn't know that 25 years ago, but now we do know that. But the other things are the fact that there is dark matter in the universe, right? Okay, this is probably just some sort of elementary particle, so you could say, okay, I don't care about that. It's extremely elusive, I have to say. Nobody's found that particle yet, but anyhow, that's kind of a technical problem. But the other thing that's really interesting now is the fact that the universe's expansion is speeding up, right? It's like somebody's leaning on the accelerator for the universe. Space is expanding not just fast, but faster every second than it was the previous second, okay? And that's due to something called dark energy, and we don't know what it is. And again, any listeners who have the insight on what this is, and have published in a refereed journal, by the way, are welcome to get in touch, because we could really use that info.
I think it's almost time to wrap up now. So my question for you, Seth, if you were arranging a great debate now for 100 years later, obviously we maybe wouldn't talk about the size of the galaxy or the island universes. What would be the topic you would choose for the Great Debate 2020?
Well, in astronomy, I mean, obviously you could debate things like, no, I'll tell you what it would be something analogous. I would say, is the idea of a multiverse, right? This is analogous to the debate 100 years ago. Is the idea of a multiverse just something with which to, you know, sell books and entertain people at dinner parties? Or is there any way to prove that it could be real?
Mm-hmm. Mm-hmm. Good. And on that note, we will reconvene in 2130, 2120 rather. Thank you very much for the conversation. That is wonderful. Thank you very much for joining us, everybody. Bye-bye.